Good evening, everyone. Today, our lecture will talk about the light emission and LEDs, and we'll learn how this process will do, and in which region will do, and why, and we will dealing with reverse bias or with forward bias, and we will learn how many types, how many kinds we have, why it's very widely using in our applications, and many informations like that. We will try to solve two examples to can learn how we can use the wavelength equation and how we can do link between the wavelength and energy band gap. Why the energy band gap is very important to us, and how we can calculate, how we can determine what color we will have with the energy band gap, and many important informations like that. Let's go from the introduction. Let's take some historical points, historical idea about this topic. This topic, we was starting to use this kind of light at 1993. LEDs are type of semiconductor, sure, called light emitting diode, which have achieved particle realization through the use of high brightness blue, developed in 1993. It's something like the last generation of light, and is the better because the efficiency, and we will know all of this information at the next slide. Here we will based on based on semiconductor types. Here we will let's go to the details. We will based on germanium nitride. They are attaching increase attention as the fourth type of light source. Like I said before, it's the last generation and the better at all light here because his efficiency, and he actually honestly he has many features led him to be the number one at our market. Yes. What is the light emission? Let an observation of light emission diode on the device which emits light by flowing current. That's mean here it share the same feature with the normal diode. Without applying current, we will not calculate anything. We will not see anything. It emits various wavelength light in the ultraviolet, visible, and infrared regions. That means we can generate lights by using the LED lights, by using this semiconductor diode light in widely spectrum, less than the visible region, more than visible region, more less than 400 nanometer, more than 700 nanometer. The energy band gap will we will control on the color we will generate it. Here, these two pictures explain to us this the anode. The lead cathode anode has two terminals here, and the PN junction diode at the middle of this small thing here. This small wire or cable. All our generation light will generate from this point, from this small point. We'll try to explain all of these questions. Let's start from what is the LED explain. LED stands for light emitted diode. Lighting products produce light up than 100%. This efficiency is great. That means here we're dealing with a small amount of losses efficiency, maybe less than 100%. That's great. That means more efficiency than than light bulbs. An electric current passes through a microchip with elements the tiny light sources we call lights, and the result will be visible light. Here at microchip, it will generate to us spectrums, lights at visible light. Start from 400 nanometer, finish to 700 nanometer, no more, no less. What cases are led to emit light? And LED bulb produces light by passing the electric current, like I said before, like the normal diode. We must apply electric current. We must do different potential through a semiconductor material, the diode, which then emits light photons through the principle of electromagnesis. The electrical resistance of the filament causes it to get so hot that it glows, producing light. This feature will be important to us. By using it, we can do great communication, compression between the ordinary diode and LED diode. LED diode generated the light directly by skipping the heating setup. What is the light emitting diode made of? Made of semiconductor diode. Like we said before here, we will depend on these two kinds of semiconductor diode, gallium arsenide and gallium phosphide. And it's made like any diode, compound semiconductor material, which are made of elements belong to group 4, 5, like phosphor will be donor, and another element doped with another elements. Group 3, like boron, will be like acceptor, and the periodic table. Here, by comparing with conventional light sources, they convert electrical light into heat and then into light. That means two steps here we have, but at the LED light, we have just one setup directly will generate to the light by skipping the heat setup, delivering efficient light generation with little wasted electricity. Because that we're dealing with little wasted electricity because it's skipping the heating setup. How do LEDs emit light? Emitting diodes are semiconductor light sources that combine a p-type, that's mean the majority are holes, and n-type semiconductor, that's mean the majority are electrons. Applying a sufficient forward voltage, we no way to dealing with reverse bias here because we don't have any chance to generate any light by dealing with reverse bias. Just with forward voltage will case the electrons and holes. This kind of reverse will lead to the electrons and holes to recombine at the active region. By this energy, we can generate LED light. Here, these two images explain to us how like I explained at the last lectures at the semiconductor course, we have valence band, conduction band, the electrons. At the last lectures here at the valence band, try to skip to the conduction band by photon or voltage or different potential or radiation, something like that will earn energy to let it to skip, run away to the conduction band. But here the situation is different because the electrons at the conduction band will come back again to the valence band. By that, it will give energy like photon, because this way we will generate light. And here we have another image. I take this picture from solar cell course. We have two different potential of energy. Number one, equal energy band gap, because that the electrons can skip to the conduction band and behind and of it hole. But here a bigger than energy band gap, because that the electron can skip far away from the conduction band, and after that we'll try to reach the appropriate situation, to stability situation, by come back again to the conduction band. By that will give to us the light power, the light we will can generate light. By the situation here, this image illustrates to us how all of them, these carriers type, can recombine at the region, at the activation region. Here, battery connected across the PN junction makes the diode forward bias, pushing electrons from the N type going to P type, and the holes at the P type directly to N type, and all of them will recombine, will stop each one at the other, and after that we will can generate the light LED from this way. Electrons and holes cross the junction and start to combine. We have many types of LEDs. The ordinary one, the normal one, we used it at the childhoods in our bicycles. Two types of LEDs are available: lamp type, lighted type, between two brackets, lighted type. Actually, not two types. We have many more than two types. That's wrong. First one, lamp type, SMD LED here. And the chip type, we saw it at our storage shops in malls. The last one, Al-Shammari LED. Let's go to RGB. Here is different and more modern from the other, I think, because here we have 4 terminals at the slip. Almostly 3 of them cathode and 1 of them is anode. At the same LED can generate different colors at the same LED, and we can use it at applications like that. Alphanumeric, we can use it at the scientific calculator, at the digital watch, and many applications like that to show the number by properly way. Here, let's do this simple comparison between the first 3 kinds of LED light. The first one is the dip light, the normal one, the ordinary one. At the same distance, this distance is 9 millimeters. Here at this distance, we can put just 9 LEDs here and 40 LEDs here, because SMD is smaller than the ordinary type. And the last one, COP, we could put 342 LEDs at the same distance, because that we can generate a great density by using this huge numbers of SOB LEDs. What is LED and its use? We will go directly to more details by using why this topic is very interesting to us, because actually this kind of light not just has high efficiency, but has many another great features. LEDs, light emitting diodes, are the latest development, the last great generation of the lights, like I said at the first slide, and the lighting intensity, made popular by their efficiency, range of color, long lifespan. But honestly, we have more we have another a great features, another qualities to this topic. We will explain it at the next slide. LED lights are ideal for numerous applications, including night lighting, art lighting, outdoor lighting, and more of that. Let's talk specifically about these applications like picture. Actually, we use this type of light in daily in our lives, and in the flash of phones, and the screen of our phones, and in many applications like that, to something like to the light to show warning something, to say you can cross the street, you can go. The ordinary light, day by day, we be far away from the last generation. Pictures, photos, and digital watches, camera flash, and automated heat lamps, digital computer and calculator, traffic signals and burglar alarm system, multiplexers. What is the meaning of light emitting? Now we will do simple comparison between the light emitting and the LED light. What the difference between them? Here is a type of a device that emits visible light, like the ordinary light, heating, and after that light, this device that emits visible light when an electric current passes through it. The LED light is a type of light emitting diode. This is very important difference. Emitting diode that emits visible light when an electric current passing through it. Both of them without current passing inside the circuit, no way to can generate any type of light here, because I used too much the visible light. I was thinking if I put this image, that will be better to explain the visible light start from 400 nanometer, finish to 700 nanometer, more than will be infrared radiation, less than ultraviolet radiation. And like I said before, we can generate many spectrum. We can generate lights at all these spectrum, at all these wavelengths, nanometers, by using diode, LED light, or LED diode. But here we focused on the visible light. Light emitting diode emits light by applying forward current to the p-n junction for a compound semiconductor. The emitted light depends on the energy band gap. By use different material, we can generate another color, another intensity of the compound semiconductor, conventional semiconductor diode. This is important. Why the conventional or ordinary silicon diodes don't emit light, but here we dealing with diodes can emit light, because the main purpose to that at the here at this topic, we dealing with diode can benefit, can generate light from the electron when will come back, when will be far away from the conduction band, and after that come back at his point at the conduction band, will emit light. But at the ordinary diode, energy becomes a thermal energy. That means that when the electron will come back to the valence band, or at the first place at the conduction band, and after that come back again to his place at the valence band, what it will give us thermal energy. Here, like I said before, the diode has two terminals, the anode, cathode. Here, substrate and layer P side, active region. Both of them, electrons and holes, will recombine on this place. How photons emitted from the lead. On lead emitting diodes, light is produced with a recombination process, like I said before, at the activation region. All diodes emit photons or light, but not all diodes emit visible light. We can generate light at visible light and at invisible light from semiconductor diode. The material in on lead is selected in such a way that wavelength of the light photons fall within the visible portion of the light spectrum. Now let's go to take specifically about this qualities of this topic. Long life. Why long life? Because the compound, that why it has longer life from the ordinary light or bulbs, because the components of the lead and the way that they generate light sufficiently extend the lifespan of these bulbs. That's depend on how generated the lifespan. Energy efficiency, high brightness and intensity, exponential color range, low radiation heat, and illumination, directional lighting, more controllability, smaller, because that one of them we could put 350 LEDs at the small distance, 10 nanometers. Here I must say something, we must note it. At the semiconductor, we known together the direction and indirection band gap. At the laser and at the diode, the LED generation, we depend on direction band gap. Now let's go to this different different idea, to some different detail between the normal p-n junction, VR p-n junction, and the VR at the light emitting diode. Like we're seeing here, we have a bigger range from the p-n junction, this diagram. Here, the reverse, or we can say the voltage potential at p-n junction starts from 0.6 to 0.7 volt, but the situation is different at light emitting diode, starts from 1.8 at IR color and finished with 3.5 volt with white color. Now, this column support my words about by using the element, that's mean we're using another, by use different element, I'm sorry, that's mean we use different energy band gap, that's mean we can generate another colors. It will change the bonds on material. This makes it possible to customize the color to meet certain wavelength specifications required for application that use traditional bulbs as light sources, like traffic light and automotive lamps. Like I said before, here we have two types of wavelength, the peak wavelength and dominant wavelength. The last one, dominant wavelength, corresponding to the color actually seen by the human eye. Here, this column is very important to us because we will try to solve two examples. One of them, it be tera hertz, that's mean exponential 12 hertz. The other one will be nano, that's mean exponential -9, and how we can convert unit to another. These two examples. Let's come back to my notes. New share. At first one, find the range of wavelength for the frequency range of visible light, starting from 400 to 750, but terahertz. By using this equation, lambda, the wavelength, equal the velocity, the speed of the light at the spectrum, at the vacuum, divided on frequency, 3 meter divided on second. Here we must reconvert terahertz to hertz, and after that divided the c divided on the frequency, our result will be 7.5 exponential minus 7 meter. To convert it to nanometer will be 750 nanometer at frequency equal 750 terahertz will be like that. The last result will be lambda equal 400 nanometer. And the last example will be calculate the following wavelength: A to germanium arsenide at room temperature, silicon at room temperature. Here we will depend on energy band gap at the room temperature. Energy band gap at germanium arsenide equal 1.43. Here 1 equal 12 electron volt. By using this equation, energy band gap, but here in joule equal Planck constant dot the speed of light at the vacuum divided on wavelength. Just here, the important thing, we must convert the energy band gap from electron volt to joule by dot 1.6 exponential minus 19 joule divided on electron volt, and after that complete our solution. Here lambda equal 869 nanometer for germanium. For silicon will be, by using the same equation, the same idea, convert the energy band gap electron volt to joule, and after that calculate it will be lambda at the silicon at room temperature 1109 nanometer. Now let's come back again. That's it. That will be the last slide. Let me explain shortly how we will do here. This type of lid is the fourth and last type and is the modern one. Started to use it from 1993. Has many features. It emits various wavelength light and all regions corresponding to energy band gap, but we focused on the just visible region, visible spectrum at this lecture to produce light up to 90-100%. That's mean great efficiency. And electric current passes through a microchip. The result is visible light here with this kind. The filament cases it to gate so hot producing light. This passes in lid circuit is forward bias, no way to dealing with for reverse bias because we don't have chance to generate any light. The light is generated due to the combine in electrons and holes at the activation region. We can delete it here and write at the active region. The COB is a smaller type because that we could put the near from approximately 350 lids and small space. But at the same time, it's strong. Conventional cyclical diode don't emit light because their combination energy, because the thermal energy. Here we gain a thermal energy, but at the diode at the lid, we gain light. The potential barrier, voltage potential barrier at the normal diode start from 0.6 to 0.7 volt, but in the lid, the diode situation is different, start from 1.8 to 3.5, 1.8 with RI color to 3.5 at last one will be the white color volt for light emitting diode. The light depending on materials used, we have two kinds of wavelength at the light, the lid light. lambda P and lambda D dominant. Lambda are used to visible light. My conclusion, this is a great type. We just have a small disadvantage. It's near from 100%. By develop this disadvantage, we can reach light, can generate light to us, be near from 100%. And this actually now it has a great efficiency. By dealing to increase this efficiency, this kind of light will be number one and will dominate on all application in our life. Thank you so much. Our lecture is done. Have a good day, and thank you for watching. Your patient.